In 1941, deep inside the Detroit Arsenal tank plant, American industrial logic officially broke down. The military suddenly needed thousands of medium tanks, but the radial aircraft engines required to power them simply did not exist. Chrysler's solution was an act of pure mechanical desperation. Engineers took 5 standard 250 cubic inch flathead inline 6-passenger car engines and bolted them together around a central sun gear. The result was the Chrysler A57 Multibank, a 30-cylinder, 21-liter, 4,600-pound iron monster that required 5 carburetors, 5 water pumps, and 5 distributors just to fire. For factory workers, it meant halting civilian lines to cast and machine an engine built like a bank vault. For the mechanics who inherited them, it meant balancing 5 distinct fuel systems in the mud. They received a logistical nightmare of moving parts. The paradox is that the A57 did not survive because it was an elegant design. It survived because elegance was a luxury American supply chains could no longer afford. But the real story of the A57 is not just a bizarre patch job. It is the story of how American manufacturing brute force turned civilian iron into the heavy power that kept a fleet moving. Every week, we document the forgotten American engines, factories, and machines that once taught the country what heavy power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story of the A57 Multibank begins not with a bold vision, but with an absolute crisis in Detroit in 1941. The story begins not with a bold new vision of power, but with a sudden, terrifying absence of it. In 1941, as the United States prepared for the inevitability of a global war, the newly constructed Detroit Arsenal tank plant was given a mandate to build thousands of medium tanks, specifically the M3 Lee and the upcoming M4 Sherman. The armor was forged, the tracks were stamped, and the assembly lines were moving, but the military faced a critical supply chain failure. They had almost no engines to put into the hulls. At the time, the primary power plant for American medium tanks was the Wright R975, a radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft. Radial engines were relatively light, incredibly powerful, and air-cooled, making them ideal for aviation. But because they were ideal for aviation, the rapidly expanding American aircraft industry was absorbing almost every radial engine block the foundries could cast. The tank plants were left waiting at the loading docks. The U.S. Ordnance Department turned to the Detroit automotive industry in a panic. They needed heavy power, and they needed it immediately. They could not wait 3 years to design, test, tool up, and manufacture a purpose-built, high-horsepower heavy engine. An engine is not just an idea. It is a system of foundries, castings, machining lines, and assembly tools. Creating that from scratch would mean stalling tank production just when the military needed it to explode. Chrysler was handed the problem. Their engineers understood that the only way to solve an impossible deadline was to use the machines they were already building. They walked onto the civilian automotive factory floor and looked at the standard Plymouth 250.6 cubic inch passenger car engine. It was an inline 6, a 6-cylinder engine arranged in one line. More importantly, it was a flathead, an engine design where the valves sit in the block rather than in the cylinder head. The Plymouth flathead was a heavy, low-revving, highly reliable piece of iron designed to pull a family sedan down an American highway at 50 miles per hour. It produced about 75 horsepower. To move a 30-ton wall of steel through mud, the military needed at least 400 horsepower. One Plymouth flathead could not do it, 2 could not do it, but 5 of them could. The idea proposed by Chrysler engineers was as crude as it was mathematically sound. They would take 5 of these standard, off-the-shelf passenger car engine blocks and arrange them in a star pattern. It was an act of situational engineering that defied traditional mechanics. The result was a 30-cylinder engine block. The total displacement, the total volume swept by the pistons inside the cylinders, swelled to an incredible 1,253 cubic inches, or roughly 21 liters. The completed assembly would weigh over 4,600 pounds. The physical reality of the Chrysler A57 Multibank was staggering. It required an entirely new way of thinking about mechanical synchronization. Engineers had to figure out how to take 5 distinct power plants and force them to act as a single unit. The 5 individual engine blocks were bolted to a massive central crankcase. Each engine retained its own crankshaft, the rotating shaft that turns piston motion into rotational power. Those 5 crankshafts were each fitted with a pinion gear, which drove a massive central sun gear. The engineering scene inside Chrysler's testing facilities in late 1941 was a chaotic blend of automotive familiarity and industrial excess. The mechanics were working with parts they recognized from civilian garages, but they were multiplying every problem by 5. The engine required 5 individual water pumps to keep the iron blocks from melting down. It required 5 separate distributors to manage the ignition timing for the 30 spark plugs. The most terrifying challenge was fuel delivery. The A57 required 5 separate carburetors, devices that mix fuel and air before the mixture enters the engine. To make the tank drivable, Chrysler had to design a complex throttle linkage that would open all 5 carburetors at the exact same moment. If the linkage fell out of adjustment, one engine would run rich, another would run lean, and one bank of cylinders would start dragging the others down, turning a power plant into a parasite. Yet, despite the inherent absurdity of bolting 5 car engines together, the system possessed a strange, rugged redundancy. If a conventional engine lost a cylinder bank or broke a major internal component, the vehicle stopped. But during early bench testing, engineers realized that if 1 or even 2 of the Plymouth blocks took damage or failed, the remaining engines could often muster enough torque, the twisting force that provides pulling strength, to keep the central sun gear turning. It would be rough and it would be loud, but it could theoretically limp a crippled tank off a battlefield. In late 1941, the first prototype A57 was strapped to a test stand in Detroit. Mechanics primed the 5 carburetors, checked the 5 oil levels, and engaged the starter. When the 30 cylinders fired, the sound was completely alien, neither the rhythmic pulse of an aviation radial nor the familiar hum of a passenger car, but a deep, overwhelming mechanical roar of synchronized iron. It vibrated heavily, it consumed massive amounts of fuel, and it was undeniably heavy. But it did not break. It held its timing, and it produced the 400 horsepower the military demanded. The prototype was running on the test stand. The next problem was figuring out how to build thousands of them without stopping the lines in Detroit. The transition from a running prototype to a mass-produced industrial reality is where an engine either survives or dies. For the Chrysler A57 Multibank, the engineering theory had been proven on a test stand, but building thousands of 30-cylinder power plants required a manufacturing breakthrough that defied everything Detroit knew about automotive assembly. To understand why the Multibank was a triumph of factory logic, you have to look at the geometry of the engine itself. Chrysler took 5 Plymouth inline-6 engines, 6-cylinder power plants arranged in a single straight line. These were flathead engines, a design where the valves sit down inside the heavy iron block rather than up in the cylinder head. Flatheads were thermally inefficient compared to overhead valve aviation engines, and they were physically wide. But they were incredibly durable, produced heavy low-end torque, and most importantly, Detroit already knew exactly how to cast them by the thousands. The core mechanical challenge was synchronization. 5 independent engine blocks meant 5 independent crankshafts, the heavy rotating shafts that turn the up and down motion of the pistons into rotational power. Chrysler engineers arranged the 5 Plymouth blocks radially around a massive central aluminum crankcase. Each of the 5 individual crankshafts was fitted with a drive gear. These 5 outer gears fed into one massive central sun gear. This single sun gear collected the torque from all 30 cylinders and sent it to the transmission. It was an arrangement that required incredibly precise machining, the industrial process of cutting raw metal to exact tolerances. If just one of the 5 engines ran slightly out of phase, it would not add power. It would act as a massive mechanical brake, fighting the other 4 engines and threatening to shatter the central sun gear. The fuel delivery system was just as complex. The A57 required 5 standard Carter carburetors, devices that mix liquid fuel and air before the mixture enters the engine cylinders. Chrysler engineers devised an intricate mechanical throttle linkage that connected all 5 carburetors to a single pedal. When the driver accelerated, 5 throttle plates had to open at the exact same millisecond. In a well-lit Detroit machine shop, this linkage was a masterpiece of geometry. But out in the field, it meant that a mechanic had to synchronize 5 passenger car fuel systems simultaneously while standing on the back deck of a 30-ton machine. The ignition system, the components that generate the electrical spark to ignite the fuel, added another layer of compounding complexity. The engine required 5 separate distributors. A distributor is a mechanical device that routes high-voltage electrical current to the correct spark plug at the exact right moment. 30 cylinders meant 30 spark plugs. A mechanic trying to trace a simple engine misfire had to navigate a dense, confusing jungle of ignition wires, 5 distributor caps, and 5 massive iron blocks. In an American service network, diagnosing a single inline 6 was a standard Saturday job. Diagnosing 5 of them wrapped around a central case required absolute mechanical discipline. Cooling the monster presented an entirely different problem. A flathead engine runs hot by nature. 30 cylinders of flathead iron bolted together inside an enclosed steel tank hull created a thermal nightmare. The A57 required a massive cooling system. The network of water jackets, hoses, and radiators designed to pull heat away from the metal. Chrysler fitted the assembly with 5 individual water pumps, moving roughly 150 gallons of coolant per minute through an enormous rear-mounted radiator. Yet despite this dizzying mechanical complexity, the true breakthrough of the A57 was not its gears or its plumbing. The breakthrough was Force 1, iron, aluminum, fuel, and manufacturing costs. The military needed power, but more importantly, it needed volume. Designing a new purpose-built V8, an 8-cylinder engine arranged in 2 banks, would take years of testing and entirely new factory lines. The A57 bypassed this supply chain bottleneck completely. Because it used standard 250 cubic inch Plymouth blocks, Chrysler did not have to build a new foundry. They did not have to design new pistons, the moving metal parts inside the cylinders pushed by combustion pressure. They did not have to forge new connecting rods, the steel arms that link the piston to the crankshaft. Inside the Detroit Arsenal tank plant, the assembly process became a surreal collision of civilian routine and heavy industrial scale. Machinists who had spent the late 1930s building quiet engines for commuter sedans were now guiding 4,600-pound, 30-cylinder, star-shaped monoliths down the factory floor using heavy overhead chain hoists. The factory floor smelled of cutting oil and hot iron, vibrating with the rhythm of mass production. Because they were using existing automotive tooling, Chrysler was able to produce these engines at a rate that traditional aviation foundries could not possibly match. The U.S. military officially accepted the design, and the fleet adoption began. But the sheer physical size of the multibank forced a structural change in the machines it powered. The A57 was incredibly long. It could not fit into the standard engine bay of an M4 Sherman. To accommodate the massive footprint, the military had to physically stretch the hull of the tank, creating the M4A4 variant. This elongation required longer tracks, altered the suspension geometry, and added even more weight to an already heavy vehicle. The engine was solving a power crisis, but it was creating new logistical burdens. When the technical manuals arrived at the fleet maintenance shops, they were thick, heavy books that would soon be stained with grease, filled with complex diagrams of sun gears and fuel linkages. The factory had solved the math of building the 30-cylinder giant at scale. The true test of the multibank would begin when that heavy iron left the clean concrete of Detroit and met the mechanics who had to keep it alive in the mud. By the middle of 1942, the Detroit Arsenal tank plant was no longer just an experiment in mechanical substitution. It had become the epicenter of the most bizarre heavy engine production line in the world. The Chrysler A57 Multibank had moved from a desperate prototype to a mandated military power plant. The engineering math had been solved. Now the challenge was sheer industrial volume. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a 30-ton machine held a front line, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. For the A57, that trust was being forged by the thousands in Michigan. The scale of the operation defied traditional automotive logic. To build a single A57, Chrysler required 5 individual 250 cubic inch flathead blocks. By the time production peaked in 1943, the factory had cast, machined, and assembled over 8 Sherman 500 of these massive 30-cylinder units. That meant Detroit foundries had poured more than 42,500 individual passenger car engine blocks solely to feed this specific heavy equipment contract. It was a staggering diversion of civilian manufacturing power. The factory floor was a deafening theater of American industrial brute force. Machinists who previously spent their shifts bolting together commuter sedans were now torquing heavy bolts on massive aluminum central crankcases. Overhead chain hoists carried the 4,600-pound completed engine assemblies, a full ton heavier than the radial aircraft engines they were built to replace. Down the line, workers carefully guided the star-shaped iron behemoths into the stretched engine bays of the newly designated F4A4 Sherman tanks. Every engine unit required a massive custom radiator, an enormous square of brass and aluminum designed to pull the heat away from 30 flathead cylinders firing simultaneously under an enclosed steel deck. The assembly process demanded a continuous, uninterrupted river of standard civilian automotive parts. Fan belts, distributor caps, water pumps, and Carter carburetors flowed into the tank plant by the railcar load. The service manuals printed to accompany these machines were thick, dense, heavily diagrammed volumes. A standard engine manual told a mechanic how to adjust valve lash or set basic ignition timing. The A57 manual had to explain how to synchronize 5 independent throttle linkages so that one bank of cylinders did not flood with fuel while another starved. It required specialized vacuum gauges and a deep, intuitive understanding of mechanical harmony. When the finished M4A4 machines rolled out of the factory doors, they filled the Detroit rail yards in vast rows of olive drab. The physical presence of the vehicle was undeniable. Because the engine was so incredibly long, the tank hull itself had been physically stretched to accommodate it, making it heavier and longer than any other Sherman variant. When a train loaded with multi-bank-powered machines began its journey toward the East Coast ports, the weight of the cargo was so immense it often required dual steam locomotives just to pull the flat cars out of the yard. But building an engine is only the first half of an industrial system. The second half is the service network, the mechanics, parts supply chains, technical manuals, and fuel depots that keep a machine running after it leaves the clean concrete of the factory. The U.S. Ordnance Department looked at the A57 and saw a long-term logistical burden. The American military preferred the Wright radial engine or the emerging twin diesel setups. They wanted engines that required fewer spark plugs, simpler fuel lines, and less downtime in the maintenance bay. Because of this, the vast majority of the A57 Multibank production was not assigned to American combat units. Instead, it was designated for the Lend-Lease program, the system where America supplied its allies with heavy industrial and military equipment. Thousands of these 30-cylinder engines were loaded into the holds of transport ships and sent across the Atlantic. They were handed over to the British military, who redesignated the machine as the Sherman von Fa. The Detroit factory had done its job. The iron had been cast, the sun gears had been machined, and the 30-cylinder blocks were crossing the ocean. The true measure of the Chrysler A57 would not be taken in the pristine testing labs of Michigan. It would be taken by the mechanic standing in the mud of an overseas maintenance depot, staring at 5-passenger car engines and trying to figure out how to make them run as one. When the British mechanics first opened the heavy rear engine doors of the M4A4 Sherman, they were confronted with a mechanical landscape that defied conventional military engineering. They did not see the neat, radial symmetry of a Wright aviation engine or the straightforward inline block of a traditional diesel. They saw a dense, intimidating wall of iron, belts, wires, and carburetors. To perform a basic engine tune-up, a routine maintenance procedure that ensures an engine is running at peak efficiency, a mechanic had to check and adjust 30 individual spark plugs. They had to trace ignition wires across 5 separate distributor caps. They had to adjust the tension on a complex web of accessory drive belts. And most critically, they had to balance 5 Carter carburetors. If the intricate mechanical linkage connecting those carburetors became bent or worn, the 5 engine blocks would stop working in harmony. One block would run too fast, another too slow, and the massive 30-cylinder unit would begin to fight against itself, sending severe vibrations through the hull. The logistical footprint of the A57 was massive. A military service network runs on spare parts. A standard tank battalion using a traditional radial engine required a specific volume of replacement parts. A battalion running Chrysler Multibanks required 5 times the water pumps, 5 times the distributor points, and 5 times the engine block gaskets. Supply ships crossing the Atlantic were loaded down with thousands of wooden crates filled with standard Plymouth passenger car parts. Yet as the British tank crews took the Sherman vibe into the field, a strange reality began to emerge. The A57 Multibank was a nightmare to service, but it was incredibly difficult to kill. The underlying strength of the engine was the simple, heavy iron flathead block at its core. Chrysler had spent a decade perfecting the 250 cubic inch inline-six for American highways. It was built to endure low-quality oil, poor maintenance, and heavy loads. Multiplying it by 5 did not erase that fundamental durability. In fact, the sheer redundancy of the system created an unexpected battlefield advantage. During heavy use, if a conventional engine blew a cylinder head or shattered a piston, the vehicle was paralyzed. It became a static target. But the A57 had 5 independent blocks feeding into one central sun gear. If one of the Plymouth blocks lost oil pressure and seized, or took shrapnel and shattered, the remaining 4 engines could often overcome the dead weight. The engine would run violently rough, the exhaust would smoke, and the power would drop. But the massive combined torque, the pulling strength of the remaining cylinders, was often enough to keep the tank moving. It could limp back to a repair depot under its own broken power. By the end of 1943, the Detroit Arsenal tank plant had pushed the A57 to its absolute peak. Chrysler was proving the brutal effectiveness of Force 1, manufacturing costs and volume. The American military needed engines faster than the aviation industry could build them, and Detroit responded by overwhelming the problem with civilian iron. The factory lines were running 24 hours a day, casting, machining, and assembling power at a rate that kept the Allied supply chain intact. Over 7,500 M4A4 tanks were built, almost entirely dependent on the multibank. In the global theater of industrial production, the A57 was a triumph. It proved that an American automotive factory could take a completely absurd mechanical concept, engineer a synchronization system to make it work, and then stamp it out by the thousands. The 30-cylinder roar of the multibank had become the sound of an uninterrupted supply line. But the engine was running on borrowed time. The factory had solved the math of production, and the field mechanics had figured out how to keep the belts turning in the mud. The machine was working. The next rival was already waiting on the drafting table, and it was going to make 30 cast iron cylinders look obsolete overnight. The decline of the Chrysler A57 Multibank did not begin with a catastrophic mechanical failure on a European battlefield. The first crack in the empire of the 30-cylinder engine was much smaller. It began quietly, written into the pages of motor pool service logs and maintenance reports. The engine was proving that it could survive the mud, but it was losing the war of man-hours. In the military service network, the global system of mechanics, parts depots, and supply chains that keeps a mechanized fleet moving, time is as critical as horsepower. When a British Sherman 5 or an American training tank rolled into a maintenance depot for a routine engine tune-up, the sheer geometry of the multibank brought work to a crawl. A mechanic trying to trace a simple misfire did not have a straightforward diagnostic path. They had to navigate a dense jungle of 30 spark plugs, 5 individual distributor caps, and 5 separate ignition coils. The fuel system was an even greater liability in the field. The 5 Carter carburetors were connected by an intricate mechanical throttle linkage. In the clean, well-lit environment of the Detroit Arsenal tank plant, this linkage was perfectly synchronized by trained machinists. But after hundreds of miles of violent, vibrating travel over rough terrain, the linkage would inevitably wear or fall out of adjustment. When that happened, one of the 5 Plymouth engine blocks would run slightly out of phase with the others. The massive engine would begin to fight itself, wasting fuel, generating excessive heat, and vibrating heavily against the central sun gear. Resynchronizing 5 carburetors on a single engine while standing on the steel deck of a tank was not just a mechanical task. It was an exhausting test of a mechanic's patience. The U.S. Army Ordnance Department recognized this burden from the beginning. They had never viewed the A-57 as a permanent solution to the American heavy engine crisis. It was always a stopgap, an act of desperate, brilliant industrial substitution. Because of its massive logistical footprint, the U.S. Army had largely refused to deploy the M4A4 Sherman in its own frontline combat units, restricting it mostly to stateside training bases and sending the vast majority of the production run to the British military through Lend-Lease. The Americans simply did not want to support a frontline supply chain that required shipping 5 times the normal volume of water pumps, fan belts, and head gaskets across the Atlantic Ocean. But the fatal blow to the multibank did not come from a military regulation or a shifting frontline. It came from a technological breakthrough happening just a few miles away in Dearborn, Michigan. Ford Motor Company had been developing a completely different kind of power. They had engineered the Ford GAA, an 100 cubic inch all-aluminum V8 engine. The Ford GAA was everything the Chrysler A57 was not. It was a purpose-built military power plant, initially designed as an aviation engine before being adapted for armor. It was an overhead cam design, an engine configuration where the camshaft is located directly above the combustion chambers, allowing for highly efficient airflow and massive power output without the heavy, restrictive breathing of a flathead block. The GAA produced a reliable 500 horsepower, easily matching the combined output of the 5 Plymouth car engines. More importantly, the physical contrast between the two engines was devastating to Chrysler's design. The Ford V8 was a single, cohesive unit. It was hundreds of pounds lighter than the 4,600-pound Multibank. It fit neatly into the standard engine bay of an M4 Sherman, meaning the military no longer had to physically stretch the tank hulls just to close the rear doors. A standard Sherman was lighter, more maneuverable, and easier to transport on rail cars and cargo ships than the elongated M4A4 required by the Chrysler engine. For the mechanics in the service depots, the arrival of the Ford V8 was a revelation. A V8 engine, an 8-cylinder block arranged in 2 banks, was something American mechanics understood intuitively. The GAA required 8 spark plugs, not 30. It required 2 magnetos, not 5 distributors. It had 1 massive water pump, not 5 smaller ones. When a tank powered by a Ford GAA needed an engine overhaul, a major service process where an engine is pulled, inspected, and rebuilt, the downtime was measured in standard shifts, not continuous days. Next to the sleek, aluminum, aviation-inspired Ford V8, the iron Chrysler Multibank suddenly looked exactly like what it was: a frantic, heavy, incredibly complicated industrial improvisation. The engineering math had been sound in 1941 when there were no other options. But by 1944, the American manufacturing machine had caught up to the demand. The foundries were flowing, the aluminum castings were perfected, and purpose-built heavy power was finally available in massive volumes. The U.S. Ordnance Department looked at the performance data, looked at the supply chain requirements, and made the only logical fleet decision. They wanted the Ford GAA, and they wanted the right radial engines that were now flowing back into the tank plants. They no longer needed to borrow power from passenger cars. The A57 had successfully bridged the gap, but as the new aluminum V8s began rolling out of the factories, the 30-cylinder giant was about to be regulated out of existence. Back at the Detroit Arsenal tank plant, the shift in military strategy translated directly into a sudden halt in heavy iron production. By the end of 1943, the mandate had changed. The U.S. military ordered Chrysler to begin phasing out the M4A4 Sherman and its massive power plant. The sprawling assembly lines that had been carefully engineered to synchronize 30 cylinders were rapidly reconfigured. The physical dismantling of the multi-bank production line was a stark reminder of how quickly American manufacturing could pivot. The foundries stopped pouring the specialized aluminum central crankcases. The massive overhead chain hoists that once carried the 4,600-pound star-shaped assemblies down the line were re-rigged to handle lighter, conventional engine blocks. The continuous, heavy flow of standard Carter carburetors, Plymouth water pumps, and distributor caps was diverted back to civilian automotive stockpiles or other standard military supply chains. The deafening, synchronized roar of 30-cylinder engines being run on the Detroit factory test stands, a sound that had defined the plant for 2 years, finally went quiet. For the engines already deployed in the field, this factory shift signaled the beginning of an inevitable collapse. A heavy military engine survives only as long as its parts network. The global system of foundries, warehouses, logistics chains, and transport ships that provides replacement components. When Chrysler stopped casting the central sun gears and assembling the specific five-way throttle linkages, the parts pipeline began to immediately dry up. In the British maintenance depots, the reality of a discontinued engine set in quickly. Mechanics suddenly found it harder to source the highly specific linkage rods required to keep the five carburetors balanced. Without these exact replacement parts, an A57 that fell out of synchronization could not be properly tuned. Motor pool crews were forced into cannibalization, the desperate mechanical practice of stripping parts from a dead or damaged engine to keep another one running. In the life cycle of any heavy machine, widespread cannibalization is the clearest indicator that the mechanical ecosystem is collapsing. The mechanics did not mourn the loss of the multibank. When the American and British forces began receiving replacement tanks powered by standard V8s or conventional diesels, the service network breathed a collective sigh of relief. The days of standing in the mud, attempting to trace a misfire across 30 individual spark plugs and 5 separate distributor caps, were over. The engine had done exactly what it was designed to do. It had bridged a desperate gap in the supply chain. But once that gap was closed, no one in the motor pool wanted to maintain a 30-cylinder patch job. When the global conflict finally ended in 1945, the American heavy engine market faced an immediate and unprecedented glut of surplus power. The military began decommissioning tens of thousands of vehicles, selling off the hardware. For a standard industrial engine, post-war surplus meant a profitable second life. A conventional heavy-duty inline-six or a purpose-built V8 could be pulled from a military truck and dropped into an American farm tractor, a sawmill, a fishing boat, or a civilian tow truck. Even the massive Wright radial aircraft engines found second lives powering agricultural crop dusters or stationary generators. But the Chrysler A57 Multibank had absolutely no civilian application. It was an industrial anomaly. It was 4,600 pounds of specialized awkward iron. It consumed massive amounts of fuel, and its dimensions made it impossible to fit inside a standard engine bay or machine shed. No American farmer was going to mount a 30-cylinder, 5-carburetor engine to an irrigation pump. No construction company was going to try and shoehorn a 21-liter, star-shaped flathead into a commercial bulldozer. The engine was entirely too heavy, too long, and too maintenance-intensive for peacetime capitalism. As a result, the A57 entered a brutal, highly efficient phase of industrial scrappage, the process where obsolete or unwanted machinery is systematically dismantled and melted down for its raw metal value. Across Europe and the United States, thousands of these incredible mechanical achievements were pulled from scrapyard tank hulls and cut apart with acetylene torches. In some American salvage yards, the giant engines were painstakingly disassembled. The 5 individual 250 cubic inch Plymouth flathead blocks were unbolted from the central crankcase. Because these blocks were fundamentally just standard passenger car engines, they were sometimes sold individually to civilians, returning to their original, humble purpose of powering commuter sedans and light pickup trucks. The operators who bought those engines likely never knew that their reliable, quiet inline-six had once been part of a 30-cylinder monster. But the rest of the A57 system was completely destroyed. The massive, beautifully machined central sun gears, the intricate aluminum crankcases, and the complex mechanical throttle linkages were tossed into scrap bins and sent back to the foundries to be melted down. The thick, grease-stained service manuals that detailed exactly how to synchronize 5 distinct fuel systems were thrown into the trash. The machine was systematically erased from the physical landscape. The engine had worked. The production crisis had passed. The military moved to purpose-built power. The civilian market had no use for it. The foundries melted the iron down. The heavy manuals were thrown away. The parts network vanished. The sound of 30 cylinders went silent. What remained was not a working fleet, but a scattered handful of frozen survivors, left to answer whether an engine this absurd could ever be understood by the generations that followed. When a conventional American engine reaches the end of its commercial life, it usually fades slowly into the background of the country. A discontinued straight-six truck engine might spend decades pulling a farm wagon in the Midwest. A retired aircraft radial engine might find a second life powering a crop duster over the Great Plains. A small two-stroke outboard motor gets tossed into the corner of a lakeside garage, waiting for the day someone finally rebuilds the carburetor. But the Chrysler A57 Multibank had no slow fade. It had no civilian afterlife. When the military contracts were canceled and the massive M4A4 Sherman tanks were decommissioned, the 30-cylinder empire simply collapsed. Today, the A57 is one of the rarest heavy American engines in existence. Because it possessed absolutely no peacetime utility, the vast majority of the 8,500 units produced were systematically destroyed by acetylene torches in post-war scrapyards. The intricate aluminum central crankcases were melted down. The five-way throttle linkages were thrown into metal recycling bins. The heavy iron was erased from the industrial landscape. The few that survived today are carefully preserved in specialized military armor museums, American mechanical collections, and the garages of extreme industrial restorers. To see a Chrysler Multibank in person is to look at a machine that breaks every rule of logical engineering. It is an overwhelming, dense wall of cast iron, heavy accessory belts, thick ignition wires, and brass fittings. To actually hear one run in the modern era is an incredibly rare mechanical event. When a restored A57 fires up, it does not sound like the refined hum of an aviation power plant or the steady idle of a modern diesel. It sounds exactly like what it is: five heavy passenger car engines forced into a violent, synchronized roar. The restoration community that keeps these few surviving engines alive faces the exact same nightmare that British field mechanics faced in 1943. Parts are nearly impossible to source. While a restorer can still find replacement components for a standard 250 cubic inch Plymouth flathead, finding the specialized central sun gear, the custom water pumps, or the exact linkage rods required to balance the five Carter carburetors requires expensive custom machining and deep archival research. A mechanic trying to trace a simple engine misfire today still has to navigate 30 spark plugs and 5 separate distributors. But the preservation of the A57 is not driven by nostalgia. No mechanic who ever had to service one in the mud wished they could go back to balancing 5 distinct fuel systems on the back deck of a 30-ton machine. The military replaced it with the Ford GAA V8 the absolute second they had the chance. The engine was incredibly heavy, it consumed massive amounts of fuel, and it was an absolute liability in a maintenance depot. Yet the multibank remains critically important because it passes the ultimate test of American industrial history. It is the physical proof of Force One: iron, aluminum, fuel, and manufacturing costs. The A57 proves that during a severe supply chain crisis, American factories did not wait for elegant solutions. They overwhelmed the problem with sheer brute force. When the military realized they did not have enough right radial engines to power their rapidly expanding tank fleets, they could have halted production. They could have waited 3 years to design, test, and tool up a new factory for a specialized heavy engine. Instead, Chrysler engineers walked onto a civilian assembly line, looked at the quiet, reliable flathead engines powering Plymouth sedans, and decided to multiply them by 5. They took the domestic machines of the American highway and forced them into a heavy industrial configuration that no engineer would ever propose in peacetime. The A57 was never meant to be a permanent design. It was a bridge. It was a mechanical patch job designed to keep the assembly lines moving until purpose-built V8 engines could arrive. And in that singular, desperate mission, the 30-cylinder monster succeeded flawlessly. It kept the foundries pouring, it kept the rail yards full, and it kept the Allied supply chain intact. Today, the Detroit Arsenal tank plant is largely gone, its massive factory floors redeveloped or demolished. The machinists who figured out how to synchronize 5 independent crankshafts into a single sun gear have passed into history. The deafening sound of 30 cylinders running on the test stands has long been silenced. The era of American manufacturing that could pivot so violently from building passenger cars to casting 4,600-pound star-shaped tank engines is over. But the heavy iron remains. Somewhere in an American museum, resting on a heavy steel display stand next to a thick, grease-stained service manual, A Chrysler A57 Multibank sits under the lights. The 5 Carter carburetors are dry, the complex throttle linkage is frozen in place, and the 30 spark plugs have not fired in decades. It is a silent, heavy monument to a moment in time when American industry proved that if a machine needed power, elegance was optional. See you in the next one.